In this video, I'm going to talk about the differences between rotational motion and circular motion. I'm also going to go through some examples of how to calculate using rotational motion equations. Please take a moment and read the success criteria I plan to cover in this video. So let's start by looking at this diagram I have here. I have the sun and the earth. Now, as the earth goes around the sun, and that would be 365 days for it to go around once, that would be an example of circular motion. In this case, we have the sun in the center and the earth just moves in a circle around it, thus circular motion. But I also have an example here of rotational motion, and that's what the earth is doing every 24 hours. We have an axis, and the earth is just spinning about the axis, not about a central point, but an axis that goes through the earth itself. So this is 24 hours, and this one was 365 days. Now, if we were doing linear motion or translational motion, that's what you would have already been calculating with. We have s being distance, initial velocity, final velocity, acceleration, and time. Now, all of those have a similar variable when we talk about rotational motion. So instead of talking about the distance that the earth went around the sun, we're going to talk about the number of angles. And that should then be in radians. And instead of initial velocity, we're going to have omega, the Greek letter, that's the lowercase, and we'll have an I for initial. So this will be initial angular velocity, and sometimes it's called angular frequency. Its units will be radians per second. And that's why it's also called angular frequency, because that would be something per second, right? Like a hertz. Now, similarly, I'll have a final angular velocity, and we'll have an angular acceleration, but we're not going to use the letter A, we're going to use an alpha, again, a Greek letter. And finally, time is going to just be the same. Oh, I forgot to put the units here. This would be radians per second squared. So notice that they all have something equal here. If I'm traveling a straight line, I'm interested in the distance. If I'm rotating, I'm interested in the angle it rotates through. And since we are talking about acceleration, I'll have initial and final velocity, and time, because it's a scalar, doesn't change. So what this does for us means that we have different kinematic equations when we're rotating. So I have delta theta is final angular velocity plus the initial velocity divided by 2 times time. If I was doing this with our translational motion, that would be the same as s equals v plus u over 2 times time. And that's something that's in the data booklet. Notice this one looks very familiar. V equals u plus at. So what you just need to be able to do is you need to be able to look at the rotating equations and be able to translate it into motion in a straight line. If you can do that, then the kinematic equations really aren't any different than the ones you already know. It just takes some practice to transfer from one, let's call it from one language to a second language. So let's go through an example. We have a card held here against a tooth wheel, and as the motor's turned on, it says it makes 3 rotations in 125 seconds. At this point, we're going to assume it's moving at a constant speed. It then is turned off and takes 14 seconds to come to rest. So what is the initial angular velocity? If we were doing this with translational motion, I would say we'd be using v equals d over t for a constant speed. Because we're using rotational motion, instead of v, I should be using omega. Instead of distance, I'll be using theta and time. So this is the number of degrees. Now I'm given 3 rotations, so I have to put that into radians. So that will be 3 times each rotation is 2 pi radians. And the time, 125 seconds. And if I pick up my calculator, I'm going to have 0.075 radians per second. What is the angular deceleration? Well, I know omega initial, 0.075. I know the final is 0 because it comes to a stop. I know the time it takes is 14 seconds. So I'm looking for alpha. Now again, if I was doing this using translational math, I would be using A equals V minus U over T. But I'm not. I'm using rotational work, so that's going to be alpha is omega F minus omega I all over T. And this will give me 6.0 times 10 to the power minus 4. It's a negative value. Radians per second squared. And finally, I'm asked for the angular displacement. So that means I'm looking for theta. If I was doing this with translational motion, this would be S. And I would try and use the equation that has these letters here. Remember, if I've made a mistake in alpha, I don't want to compound it in my next one because it might give me some really weird answers. So I'd be looking for S equals U plus V over 2 times T. So theta is going to be 0 plus 0.075 over 2 times 1.25, giving me 4.7 radians. Okay, let's do one more example. A ball is attached to a string of 1.2 meters and rotates in a circle. It's going to make 2.1 revolutions per minute. What is the angular velocity? Now, this says 2.1 revolutions per minute, but if I want the angular velocity, this should be in radians per second. So, 1 revolution is the same as 2 pi radians. Notice how I've written them so that the revolutions will cancel out. 1 minute is the same as 60 seconds. Again, I've written these so that the minutes cancel out, and my units are now going to be radians per second. And this is going to give me 0.22 radians per second. Now, what is the tangential speed of the ball? So now we're talking about circular motion here. V equals omega r. Omega being the angular velocity at which it's rotating about this point. So I'm going to say 0.22, it's its angular velocity, because it's in radians per second, times the length of that string, 1.2, because we know the longer the string, the faster its tangential speed. And this is going to give me 0.26 meters per second. Now that we know its angular speed, we can still use this to calculate the angular displacement. So we're looking for theta. A constant speed. I'm looking for the angles or the distance traveled, and we have a time. So if I was doing this with linear motion, I would say V equals d over t, but we're not, so I'm going to say omega is theta over t. Moving that around, theta will be omega times t. which will be, don't forget it needs to be the omega, times the time. It'll give me 7.7 radians. Not degrees, but radians. Note that sometimes they'll also ask how many revolutions would this do, so if that was the case, I would divide this by 2 pi. Or if I wanted to change it into degrees, I would divide it by pi and multiply by 180. So please take a moment again to read the success criteria that I hope you can say yes to after watching this video. Testing of the size